we're looking at something now. We've identified both kinetic and potential energy and what they represent. So let's review just a little bit here. Kinetic energy is always the energy of what? Motion. Has to be energy in motion because it's got velocity in it. Okay, so it's got to be in motion. If it's not in motion, it does not have kinetic energy. Okay, then we talked about potential energy. Give me the overview of what potential energy is. There's two types, right? Gravitational and spring. But what is potential energy at its most core concept? Bingo. It's stored energy. So potential energy is what you have the potential to do. Okay? So we looked at spring potential energy and gravitational potential energy. Okay? But what we have to understand is that at most points in any object and in its path, it could have both types, right? We looked at the roller coaster and how that applies as something's moving through the roller coaster. Sometimes it's got kinetic, sometimes it's got potential, but sometimes it has both. And so when it has both, it's called, the total sum of that energy is called its mechanical energy. Okay, how much energy it has in total is called its mechanical energy. And at any point, it could consist of all kinetic or all potential or a combination of both. Okay, but the mechanical energy of it does not change. Okay, think of it as a pie chart. This would be the 100%, and it's broken down into some combination of those two things. Okay, so at some point it's got that. But that's the basic equation for mechanical energy. So now if I was looking at to find just the energy of an object at the highest point, let's say it's on a roller coaster, if I wanted the mechanical energy at this point, that means my kinetic energy would be 0. So essentially, I'm just solving for the potential energy of the object at that point, right? Because I'm at rest, so my mechanical energy would be equal to my potential energy. Okay? All right, so that's all it says. We can combine the energies to form one equation for the conservation of mechanical energy. So remind me what conservation of energy says. Right, can't be destroyed or created. And so when we combine this energy equation into one to solve for the conservation of energy, that says that our initial energy of our system is equal to the final energy of our system. Okay, that's what conservation of energy says. Okay, is that the energy at the beginning point of my system is equal to the energy at the end of my system. So the 1 and the 2 kind of represent initial and final. Okay? Now, when we're looking at this big equation, this boxed one is the one I think you should have on your equation sheet. Okay? This is just saying initial energy is equal to final energy. This breaks it down into kinetic and potential. But then this one really is the one that shows us all of those broken down. Okay? So this 4-term equation is one I think you probably should have on your equation sheet. Okay, what type of potential energy is represented in the equation right now as it is? This is gravitational potential energy. Okay, this is gravitational potential energy G, potential energy G. So if I was looking at an object that was elastic potential energy instead of gravitational potential energy, my equation would look like this. I would have 1/2 mv squared plus 1/2 kx squared. And on the other side, I would have 1/2 kx squared as well, right? If I was looking at an elastic potential energy situation instead of gravitational. So you could have this equation on your equation sheet if you want as well. That's up to you, okay? So it's either this one, which tells us about springs, or the one I showed first was about gravitational potential energy. Do you understand the difference between those two? Mm-hmm. Okay, do you see a situation in which we would need to use both spring potential energy and gravitational potential energy? In what case would you have maybe both?
Mattress.
Okay, yep. Trampoline, bungee cord, right? Any of these things that are vertical springs. I could have a situation in which I would need a 6-term equation. Kinetic plus gravitational potential plus spring potential equals kinetic. You know, it's very rare that you would use all 6 of those terms, but you could have an equation that might involve all of them. Does that make sense? So vertical springs would need you to account for both gravitational potential energy and spring potential energy.
So why is it again that we like that?
This would be as if my situation was a spring. So if I had a spring that was loaded, and I wanted to know how much motion that caused, I would use this one.
Do you think that's good to put on?
I think you should have maybe both of those on there, okay, on your equation sheet. I'll go back to the MGH one here in just a second. But this one you would use for springs. The other one you would use for gravity.
And would it still be labeled as like 1?
Yeah, the 1s and the 2s are just helping us to think about final and initial. I always, when I do my problems, I always just make the left side of my equation the initial and the right side of my equation final. Right? Realistically, it doesn't matter what side of the equation they're on as long as it's consistent in both ways. Okay, so this is the spring one, and then your MGH one is the potential energy of gravity. Okay? So let's go ahead and try some here. Okay? I want to remind us one point here about the transfer between kinetic and potential. So just before an object hits the ground, all of its potential energy has been converted into kinetic energy. So when we're looking at objects that say, what was the speed as it hit the ground? We're remembering like what we did in our kinematics chapters, that we're not talking about after it hits the ground and comes to a stop. We're talking about the instant before it hits the ground. So at that point, at the instant before it hits the ground, we're assuming that all of that energy has been converted to kinetic, even though, we might be millimeters off the ground or whatever. Okay, so we're going to keep that true. So this says we're at a height of 3 meters. Here's my stone. This is 3 meters. It's going to fall downward, but not all the way to the ground. It's going to fall to a height of 1 meter. So we're really looking at what's its velocity at this point. Okay, we want to know how fast is it falling at that point right there. Okay, so the first thing we've got to determine is at the beginning, at the very top of its motion right here, what type of energy does it have? Kinetic, potential, or both? Only potential. Okay, so we're just talking about all potential at this, all potential right here. Okay, what about at this point, at the 1 meter mark? It has both. Okay, it has kinetic and potential. And that's because we're not falling all the way to the ground, right? If our object was falling all the way to the ground, we would have transferred it to purely kinetic, but that's not the case. So when I set up my equation, right, kinetic plus potential equals kinetic plus potential, right? This is the before and this is the after. We said that before we don't have any kinetic energy, right? We said we have all potential. So really we're just going to drop that term out of the equation. When I do the problem, I like to put in a 0 for kinetic energy so I know that like I accounted for it and I thought about it, but it's realistically it could be left out. So I know I have 0 kinetic energy plus potential energy. So what's the equation for potential energy of gravity? mgh. And were we given a mass anywhere in the problem? No, so we're going to hang on to that for a second. We're just going to put it in as an m for right now. We're going to leave it as an m. So m times 9.8 times the height, which our original height was 3 meters. Okay, this whole left side of the equation is my initial. Okay, then on the right side, I do have kinetic and potential, so I'm going to put them both in. 1/2 m, and I'm solving for v, so I'm going to keep that as v squared. And then I'm going to keep my m, because I don't know my mass of my object, times 9.8 times our final height, which is 1. Okay, now we're going to work through the algebra, and you're going to see that your m's end up canceling, right? We're going to work the algebra, and your m's will end up canceling out, but I want you to see it first, okay? Sometimes when it gives you a mass, you plug it in. If it doesn't, it's really not that big of a deal, but I'm going to show you how that works. So on the left, that leaves me with, I don't know, what's 9.8 times 3? 29.4 m equals 1/2 mv squared plus 9.8 m. So how we're really solving for velocity here, right? This is really the variable we're looking for. How can I start getting that by itself? Right, I'm going to combine my like terms, and I'm going to move 9.8 m to the other side. So I'm going to subtract that over here. The m is still attached. That leaves me with 19.6 m equals 1/2 mv squared. So now we've got pure multiplication on both sides, which means what can we do with the m? Yeah, I could divide by m on both sides, but I'm just going to cancel it. Right? So that leaves me with 19.6 equals 1/2 v squared. 19.6 equals 1/2 v squared. So what's the algebra I should do to get that across? Divide by 1/2. So divide by 0.5. And then I will square root. Perfect. Second square root, that answer. And that gives me a velocity of hold on. Okay, yeah, I had something plugged in wrong. Then I'm going to square root. So what do we get? 6.26? Okay, so now I've got to pay attention to, is my object moving up or down? Down, so I have to add the negative there. Negative 6.26 meters per second. Assuming the height of the top hill of a roller coaster is 40 meters and the car starts from rest, calculate the speed of the car at the bottom of the hill. So I like to draw a mini little diagram here just to give me an idea of what's happening. You don't have to necessarily, but here's my roller coaster, right? And I want to find out what's its velocity here. Okay, now I need you to realize, like, this roller coaster track probably sits so far off the ground, right? It probably does. But in all reality, what we're looking at here is how fast is it going at that point on the track. We don't need to know how fast it would go if it fell to the ground. So when we do these problems, you get to kind of set where your baseline is, right? We're going to call, like, that bottom of the track, that's our 0 point. Okay, so really at this point up here, what type of energy do we have?
Potential.
All potential. And then at the bottom, what type do we have? All kinetic, right? We're not going to say it could fall further. We're keeping that as our kind of our ground. So as I'm setting up my equation, then I've got 0 kinetic energy to start. And then what type of potential energy are we working with? Gravity or elastic? Gravity, right? So I'm going to have 0 kinetic plus potential, which is mgh, equals kinetic 1/2 mv squared plus 0, because we said we had no potential energy at the end. Okay, like I said, I like to put in the zeros so I know I've accounted for all the terms, but you don't necessarily have to do that. Again, our m's are left in there, so 9.8 times 40, gives me 392 m equals 1/2 mv squared. And now my m's will cancel, right? Because I've got them in multiplication terms on both sides. 392 divided by 0.5 gives me 784 equals v squared. And then I'm going to square root both sides to get v by itself. Thank you. 28 meters per second. So on roller coaster problems, I know it's it's different because it's going forward and down, right? So when we use things on tracks, I typically just kind of imagine our velocity as forward moving so you can keep it positive. I would not take it off if you would count it negative, if you would put a negative on that, because technically it is rolling down as well. So on roller coaster type problems, I'll kind of accept either direction. But in free fall problems, that's where you have to be careful and add the negative, okay? But things on tracks, I kind of think of them as just moving forward, right? Because they're really not going to move backwards. Okay, let's look at the second part of this question. It says, at what height will the car have 1/2 of this speed? At what height will it have half the speed? What's your first intuitive guess?
Halfway down.
At halfway down, right? So we will see if that works. Okay, but how do we get to that point? Okay, so here's what we're going to do. We want the car to have half that speed, which means if we're looking at our diagram again, right, if we've got our roller coaster, we're starting at the top. And at some point in here, we're going to have a velocity of 14 meters per second, right? Because that's half of our top speed. So we want to find at what height are we going to have a velocity of 14 meters per second. But at any point in here, what type of energy do we have? We've got kinetic and potential. So let's set it up again. At the beginning, we've got no kinetic plus potential. And at some point along the way, we've got a speed of 14, but we want to know the height. So we're looking for the height at which my vehicle is traveling 14 meters per second. right? That whole right side of the equation is connected. So again, your masses are going to end up canceling. So you can do that earlier if you want. But you can leave them in there if you prefer to. It doesn't really make a difference. So 392. So I left my m's. I'm going to combine my like terms here. So now my m's will cancel. I'm going to take 294 divided by 9.8. Gives me a height of 30 meters. So not halfway, right? Realistically, when do you gain most of your speed? So, okay, so 30 meters, remember that's not 30 meters down, that's 30 meters from the bottom. So you've only traveled a quarter of your distance, but you've already gained half your speed. So think about on a roller coaster, don't you feel that initial rush at the beginning? Right? That's why that is, right? It just has to deal with its energy. And that's a lot of because of that square, right? That has to deal with how quickly that ramps up. But that's why you feel a big rush at the beginning. It's not a constant speed down there. You get a lot of your energy and your speed right at the beginning, and then it will kind of even out as you go down that hill. But remember that 30 meters is 30 meters from the bottom. It's not how far you've traveled there. So